Okay guys, let's talk about Lewis structures. The first thing we have to know is how many electrons do we have to deal with, and so we need to know what elements we're dealing with and then count the valence electrons. We've talked about valence electrons a couple of times, so let's start with let's do something like methane. Methane is natural gas. It's what you find in your stove, or here when we use Bunsen burners. It's a very good fuel. So we have carbon and hydrogen. So I have one carbon, and every carbon has 4 valence electrons to give me 4 there. Hydrogen, I have 4 of those. Since hydrogen is in row 1 of the periodic table, or column 1 of the periodic table, it has 1 valence electron, so that gives me a total of 8 valence electrons. And so we typically in a formula put the atom that will be in the center of the molecule at the beginning, and then the atoms that will be on the outside of the structure are listed next. So we are going to put carbon in the center, and we will put the 4 hydrogens surrounding the carbon, and we have 8 valence electrons to deal with, and we need to connect our atoms. So we would connect our hydrogens to our carbon, and let's see how many electrons we've used, how many we have left over. And so I have 2 electrons here, 2 here, 2 here, and 2 here. That gives me 8 electrons that I've used. I had 8 valence electrons to start with, and so I've used up all my electrons. I don't have any left over, and so this would be my Lewis structure. Let's go ahead and try something else. How about water? Let's try water, H2O. Now this is an unusual structure in that we don't put the atom we're going to put in the middle first, but hydrogen we know has to be on the outside. So the atom that's different is the one that will go in the center. And so oxygen will be in the center. I have 1 of those, and oxygen has 6 valence electrons since it's in the 6th column of the periodic table. Hydrogen, I have 2 of those. It's in column 1, so that's 1 valence electron for 2, so that gives me again 8 valence electrons to deal with. I would put oxygen in the middle, connect each hydrogen to it, and I've used 2 electrons here and 2 electrons here, so that's going to be -4. I have 4 left over. I will put 2 pairs of electrons on oxygen, because again we want to satisfy the octet rule, especially for oxygen or any main group elements. Hydrogens only have 2 electrons, so they're never going to satisfy the octet rule. And if they have 2 electrons like this where they're sharing them, then they're satisfied. Let's try something like ammonia. Ammonia is NH3, and I'm going to go ahead and pull this sheet off. And let's do another one. So NH3. So I have nitrogen, hydrogen, I have 1 of those, I have 3 of those, and nitrogen is in the 5th row, so it has 5 valence electrons, again 1, for a total of 8 electrons. And we put the nitrogen in the middle, connect the 3 hydrogens, and we have used 2, 4, 6 electrons. That leaves 2 left over, which is good because I need more electrons for nitrogen. Right now it only has 6 valence electrons, 2, 4, 6. We want it to have an octet, so it needs 2 more electrons, so we would put a lone pair on the nitrogen. What about something that would have a double bond? I talked about ethene, which is C2H4, and so we have 2 carbons, we have 4 hydrogens, 1 electron there, 4 electrons there, so that's 8, that's 4, so we have a total of 12 electrons. We are going to have the 2 carbon atoms connected in the center. Okay, so we have 12 electrons. We are going to connect the 2 carbon atoms to each other, and we are going to evenly distribute the hydrogen atoms to each carbon, so that would be 2 hydrogen atoms per carbon atom. And so we get a structure like this, and we have 12 electrons. We've used 2, 4, 6, 8, 10 of them. Now we want to look, and we see we only have 2 electrons left, but this carbon atom has 2, 4, 6 atoms, or electrons. This has 2, 4, 6 electrons. We do not have enough electrons to do a lone pair on each carbon, because that would require 4 electrons. So instead of putting a lone pair on this carbon or on this carbon, we can actually make a second bond between the 2 carbon atoms, so that we would have 8 electrons for each carbon, but not exceed our electron count. So we have 2, 4, 6, 8, 10, 12 electrons, which is the total number of electrons I have to use. And then I have 2, 4, 6, 8 for this carbon, and I have 2, 4, 6, 8 for this carbon. And so that's the only way to both satisfy the octet rule and not exceed my electron count. I think we need another example. So let me do one for acetylene. Acetylene is ethine, which is C2H2. Wow, we don't have many carbon atoms, or not many hydrogen atoms anyway. So I have 2 carbon atoms, each have 4 valence electrons for 8. I have 2 hydrogen atoms with 1 electron each, which gives me a total of 10 electrons. Again, the 2 carbon atoms would be bonded. Each hydrogen atom would be distributed evenly to the carbons, and I get this. And I've used 2, 4, 6 electrons, which leaves me with 4 electrons. I could put 1 pair here and 1 pair here, but that would only give me 6 and 6 for each carbon. And so that's not going to work. Let's put a double bond in. So now I have 2, 4, 6, 8. I've used a total of 8, used 2 more electrons, so that gives me 2 electrons left. And I've got 2, 4, 6 for this carbon and 2, 4, 6 for this carbon. Again, 1 pair of electrons left. I can't put a lone pair on one side or the other, or I don't get an even count. And so I'm going to have to actually put in a triple bond, and that uses my last 2 electrons. And I've got 2, 4, 6, 8, 10 electrons, so you want to make sure you always count up your electrons when you're done. Make sure it equals the number you had to start with. And then you want to check that each atom satisfies the octet rule. So we have 2, 4, 6, 8 for this carbon and 2, 4, 6, 8 for this carbon. Now let's do exceptions to the octet rule. And exceptions are something like boron, and this is borate, or no, I'm sorry, this is hydrogen boride. And so we have 3 hydrogens, 1 boron. So boron, I have 1 of those. They have 3 valence electrons. Hydrogens, I have 3 of those with 1 electron. And I get a total of just 6 electrons. Again, boron would go in the center. And we get hydrogen, hydrogen, hydrogen. And we've used 2, 4, 6 electrons. We've used up all of our electrons. And we actually end up with boron having fewer than 8 electrons on the central atom. Let's look at something like, trying to think of an easy phosphorus compound. One is not coming to mind. How about sulfate? And this also brings up the charge issue. So sulfate is SO4 2-. So sulfur, I have 1 of those with 6 valence electrons. Sulfur, I have 4 of those with 6 valence electrons. That's 6 and 24 for 30 electrons. But this -2 charge tells me I have 2 additional electrons that I don't have naturally with these 2 elements. They've added 2 electrons from somewhere else, maybe from a hydrogen or some other atom, and so I have to add 2 electrons to my count to get a total of 32 electrons. So sulfur will be the central atom because it's unique. I'm going to attach each of my 4 sulfurs, and I've used 2, 4, 6, 8 electrons, and that leaves me with 24 electrons. So let's put all these guys up to 6 electrons just to kind of get everybody to the same area. And I like to go to 6 because then I I know I may have to do some multiple bonds or something. So I've used 2, 4, 6, 8, 10, 12, 14, 16 of these 24, so that leaves me with 8 more electrons. Now, I could put 2 electrons here, 2 here, 2 here, and 2 here. But then I would have a lot of positive charge on the sulfur and all these negative charges on the oxygens, and that has to do with formal charge, which we will talk about in another video. So you're going to just have to trust me on this one, that we would make actually a double bond here, a double bond here, and then we would put 2 pairs of electrons there, and that used up 2, 4, 6, 8 more electrons. And if we count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32. So I've used my 32 electrons, and we'll talk about formal charge in another video. But I think that's plenty for now. We'll do more of these in class. We'll talk about all your questions then, so make sure that you have all of your questions ready. Otherwise, we'll do problems in class. Bye.